So I'm most grateful to the organizer for inviting me, especially because I'm an experimentalist, and my experiments are not in quantum physics, but in classical physics. So my collaborator in this work were Stéphane Perrat, Mathieu Labousse, Marc Mesquin, and Emmanuel Faure. And the title that I gave was a bit short, so I made it a little bit more precise here. And I will discuss the emergence of observable microscopic eigenstates for single particles that have a wave-mediated interaction with their own past. So the object I'm studying is this. So this is a small film to show you. So I talked about this already, but some of you might have never heard of it, so I have to give a short summary. So I'm studying bouncing droplets on a liquid bath. So this is what the object of my study. So you have a droplet of oil bouncing on an oil bath, which is vibrated vertically. And so the reason for which the drop bounces is that it is protected by an air film that separates it from the oil bath. And the bath, because of the oscillation of the bath, each collision of the drop with the surface generates a wave field. So obviously it's not a quantum system. It is macroscopic, it is two-dimensional, it is dissipative and sustained, and it has a fixed frequency, and finally an ether. But however, we do see sort of quantum-like behaviors, and it's interesting to study them because it's very far from quantum mechanics. So we don't study this system because it is close to quantum mechanics. We know it's not close to quantum mechanics. It's far from quantum mechanics, but maybe it's interesting to study as such. The other advantage of this system is you can observe it in two ways. You can have measurements that are non-intrusive because light doesn't interfere with any of the phenomenon. So you can look at what happens, but you can also do intrusive measurements. That is whenever you use drops or waves or boundaries to perturb the system. So I will speak about only two things. One is the wave field, what is the nature of the wave field, and I will show you that it's dominated by an effect of memory. And then I will discuss behavior when the trajectory is confined, and in that, you can do many different things, so I will briefly show you films about this, and then I will discuss uniquely the orbiting in a central force field. So when is walking observed? So you have this shaker, you have a small bath of oil, you shake it vertically, the drop bounces on the surface, and you have two parameters, many parameters are fixed, but you have two relevant parameters, the size of the drop and the amplitude of the oscillation. So this is a phase diagram of the behavior as a function of size of the drop and acceleration. Most important is acceleration. Below this threshold, there is no bouncing. In all these regions, there is bouncing. Now, in this region, which is marked F, then the bath becomes unstable to a very well-known phenomenon, which is Faraday wave generation. So it's an instability that was discovered by Faraday, and whereby you have forcing of surface wave, parametric forcing of the surface wave by the oscillation. So the interesting phenomena occur here. So the Faraday wave would be generated if you were just above the threshold, but you are below the threshold, you are in this region. And in that case, the drop bouncing is sufficient to generate localized mode of Faraday waves. And this is the main trick. So this phase diagram has been is now very well understood, and the fluid dynamic part of it has been studied by Jan Moracek and John Bush in MIT. So the resulting object is interesting because it couples a localized structure, which is a drop, and a huge wave field. And they have to live together, because if the drop breaks, the wave disappears. And if the wave is damped, then the drop stops. So the walker is an entity that couples the drop on the wave field. And the interesting question is, what is its dynamics? So I will go into more detail on the wave field structure, because it's a fundamental feature of this object. So what is the wave? So as you have seen, this wave field results from the bouncing. So the drop is moving from bottom to top here. And this wave field has been generated in the previous bounce of the drop. And what is its structure? So in order to understand it, instead of studying the repeated bouncing, iterative bouncing, you study one bounce, or rather you study one disturbance of the surface. So you drop a small steel ball in a bath, so it's just like throwing a stone in a pond. And the normal reaction is that you have a wave propagating away from the point of impact. This is what you will get when you throw a stone in a pond. Now, this is without periodic forcing. If you have a periodic forcing of the bath, then the initial wave is the same, the propagative wave is the same, but it leaves behind a structure of standing waves, standing Faraday waves. These standing Faraday waves will be damped in time, but on a long time scale. And in fact, this time scale of damping will depend on the distance of Faraday's threshold. So from this, you can build a model of the wave field, saying that at each bounce of the drop, you generate a order zero Bessel function, and that they are damped on a typical time tau. This time tau depending on the distance of Faraday's threshold. And then you add a condition that the velocity of the drop is linked. So the drop moves because it falls on a slanted surface created by the wave. So there is a coupling of the wave field and the motion of the drop by this intermediate. So this is the iterative motion of the drop. So this very simple model is sufficient to produce the spontaneous walking of the drop. And furthermore, it reproduces very nicely the structure of the wave field that you observe. Incidentally, this is a Fresnel interference structure due to the fact that the sources are lined, the sources of waves are the points that have been visited by the drop in the past, and they are lined up on this half line here. So this is exactly a Fresnel interference pattern. So the interesting thing in this experiment is that you can tune the memory, that is, you can tune the time during which the waves survive. If you are far from a Faraday instability threshold, the waves are very quickly damped, so the memory is weak, and the wave field is very simple. If you are very near the Faraday instability threshold, then there is a superposition of many, many waves emitted in the past. So I will, so in a way, you have two systems. You have two objects. One object is a low memory object, where you do have a walker which walks at constant velocity and which is coupled to a wave field. And you have a high memory object which has the same property, but the wave fields are completely different. So in the following, you will see a strong distinction between what happens at low memory and what happens at high memory. So this is just how do you tune the memory. You go from A to B to C, which is the Faraday instability threshold. Okay, so it's interesting to note that this system implements a sort of memory system in the sense that at each bounce, the drop records something on the surface. It records the point at which it has collided with the surface. The memory of this collision is sustained by the wave. Then there is a global wave field, which is a superposition, linear superposition of all these waves. And at each collision, the droplet reads the cumulated memory by looking at what is the local slope of the interface. So this is very non-Markovian. So I will just show you on the films what is the effect of confinement in a circular cavity. We have studied this case, but I don't have time to present both systems. I think the second one is even more interesting. So I will just show you what happens. So you have here a circular cavity. The drop is confined inside it. It's a low memory situation. The wave field is very localized. And what you see is a very simple motion. The drop is repelled by the boundary and does a simple orbiting around in the cavity. Now, if I go to high memory, So it's oh, sorry, I missed. If I go to high memory, so the system is exactly the same. The excitation is just a little bit higher, so so all the waves that you see here have been generated in the past by the drop. If the drop breaks, everything will be back to a flat surface. And as you see, the motion of the drop becomes highly disordered. Okay, you can understand this by this film. So this is just to show you how the wave film forms. So in this particular case, I've put a drop on the side of the cavity and let it go inside the cavity, and you'll see the evolution of the wave field. So you see the drop initially as a rather simple wave field, but then the waves are reflected by the wall, and the drop comes and visits areas that it has already disturbed in the past. And of course, this disturbed it, and the motion becomes complex. So now I'm coming to the main part of my talk, which is the orbiting in the central force. So the most generic situation, in a way, is to apply to the drop a force, a central force. So this is not so easy. You have to put in the drop a small drop of ferrofluid, and you magnetize this drop of ferrofluid by a constant magnetic field. So the drop becomes a small magnetic dipole. Then you create a small gradient of magnetic field so that the drop will be submitted to an attractive central force. So this is a sketch of the setup with the coils generate the global field, and the small magnets create the gradient. Okay, so the idea, the interesting possibility of this experiment is that the distance of the magnet to the surface can be tuned, and by doing so, you change the potential well in which the drop is moving. And why is it interesting? Because you see, in our system, this was already shown this morning, so this is a quantum potential well. In a quantum situation, you know that you have different levels of different energies and different wave vectors. In our system, we cannot do that because the drop has a fixed wavelength and a fixed velocity, so you cannot change. So we always thought that it was hopeless to see any quantization of energy with this system. But the trick here is that instead of working in a constant potential well, we tune the potential well, and we seek, are the eigenstates, when I change the potential well? Do I see them pass by? So this is what we did. So this is a short memory situation. So the drop is trapped in a potential well. With short memory, all the orbits are circular because the velocity of the drop has to be constant. And its radius is given by the classical law saying that the centrifugal force is given by is equal to the centripetal force. And there is a slight corrective factor due to the wave, but it's a continuous one. Now, if I go to a higher memory, so this is a different diagram as a function of memory. And as a function of memory, you see that while I could have any radius before, at high memory, the radii that I can get are discrete. And these are the different orbits that I observe. So these are discrete circular orbits. And if you wish, we have reached what we wish to do, which is to see eigenstates pass by when we change the potential. So I forgot to say, this is the width of the potential well. So this is a control parameter, experimental control parameter. Now, the interesting thing, so these are the orbits, circular orbits. They can be either completely stable or wobble, but they're still, if you look in detail, they're still circular orbits, wobbling circular orbits. But the interesting thing is that they are not the only orbits that you see. Some new orbits show up, and they exist only at high memory. Some of them are lemniscates, some of them are trefoils, and there are still other structures of that type. So again, they can be stable or wobbling. Now, interestingly, all these trajectories, lemniscate, trefoils, and so on, can be fitted by Cassinian ovals. Now we want to compare this trajectory. We want to compare the circular trajectories with the non-circular trajectories. So we measure two things, a mean radius, and on the mean angular momentum, the average being taken on one orbit. And you try to look as a function of the control parameter at the values of the mean radius and the mean angular momentum. As you see, the mean radius is discrete also for the lemniscates and the trefoils. And as it happens, the lemniscates are lined up with a second circular orbit or with the fourth one. And as you see also, of course, the lemniscates have a zero angular momentum since it's rotating one direction and then the other. So it's more interesting to plot, instead of plotting R as a function of the control parameter, you can try to plot R as a function of LZ. And in that case, you obtain this. So you see that all the possible orbits that we see are from discrete clusters in this diagram. And as you increase the radius, which is something like the energy in quantum mechanics, not exactly the same, you see that you have circular orbits. Then you have the possibility of circular orbits or lemniscates. Here you have circular orbits, and these are, I didn't show them, but they are sort of off-centered small orbits. And then at the fourth level, you have these five different states. So note that this is scattered because at this point the orbits are big, and the potential well is not so harmonic anymore. So you can try to find why does this occur, and it's linked with the fact that you have confined the particle. So the particle visits a finite area, and you can imagine that since it's bouncing all the time, it will finally excite eigenmodes of this area. So this is what we have tried to do. So you can, these are computed wave field with high memory. So here it is computed with taking sources that are aligned on the trajectory. But you would like to express this field as a function of the eigenmodes of waves that are centered at the center of the orbit. And this is possible because there is a theorem by Graf that permits to project Bessel function from one center to the other, and with the result that you find that in this system, the amplitude of the central waves which will be excited depends on where you bounce. So this can be seen here. You can see here on this photograph that the moving drop excites a central field. This is even better seen on these films, where you see this is very high memory, and you see that the orbit is still circular because the particle moves in a central field, but there is a good agreement with the zero of the Bessel function. Okay, so maybe I will skip this. This explains just how I can answer to question how this bouncing generates plateau on these discrete levels for circular orbits. And you can do the same analysis with lemniscate, and you find that in lemniscates you excite only very few modes of the central field, and that everything is dominated by the mode J2 and J4 of the Bessel functions. Now let's come back to the general situation. I showed you stable orbits. But if you don't do a fine-tuning of the control parameter, this is not what you get. What you get is this. So you get a very disordered pattern, the same that you have seen in the cavities. And this looks extremely complicated. And it is the most general solution. But if you look in detail to those solutions, and particularly if you record the time evolution of angular momentum along this trajectory, you find that it has periods of stability on some orbits that are either, in this case, lemniscates or circular orbits. And in fact, if I look at the yellow region here, it corresponds to this yellow trajectory here, and the pink region here corresponds to the pink lemniscate here. So in fact, that's a very important point, is that the system can only be in one of these discrete sets. It is at any given time, the system is only in one of these states. And the probability of these states is well defined. This is a PDF of the probability of being in a left-turning circle, lemniscate, or right-turning circle. So in fact, so here is the control parameter. If I change the control parameter in the forbidden range, that is in between this pure lemniscate mode and this pure circle mode, I find a changing probability of being in each of the states that you can see here in the trajectory, which are a mixture of or a superposition, rather, of the two states. And these are the time recording. And now if I look at the probability of being in a lemniscate state or in an orbital state, I see that the probabilities change continuously, and that the sum for any given value of the parameter is 1, which means that the time spent in transition is small. Okay, so this is when the same phenomenon is observed whatever the memory, but a typical time of intermittency. So for those who are used to nonlinear physics, this is a typical intermittency between two states, and the typical time of the intermittency decreases when the memory increases, but you still retain the same mixture of eigenstates. So this is for a very high memory, and the mixture becomes a little bit more complicated. This is again a case of intermittency showing these are more for the amateur of nonlinear physics. This is very nice signal of intermittency, and you can do tricks of nonlinear physics like Poincaré map, and you find that this is somewhat similar to Lorentz attractor. So the conclusion. So the main point, I mean, the experiment is nice, but the main point is not that you have a bouncing droplet and so on. The main point is that this object permits the exploration of a different type of dynamics, because what I call a Walker or self-surfer is associated with a continuous memory of the past, of its own past, by the waves that it has stored in its wave field. So it is not a retarded effect. Usually a retardation effect have a finite time of the retardation, so you have what happens at time t depends on what was at time t minus tau. Here it is not that. It is that what happens at time t depends on all the past, if you are at the infinite memory. So it leads to self-organization. Usually people think of self-organization as something that you see when you have many objects that interact and do some special dynamics and self-organize in that way. In this case, you appear to have self-organization with one single object because it interacts with its own past, with all the sources that are left previously. And as it turns out, so I've shown only one experiment today because I didn't have more time, but all the quantum-like properties that we see in this system are all linked with this wave-mediated past memory. So it creates a very specific type of temporal non-locality, and we believe an unexplored type of dynamics. Thank you.
So, okay. Thank you very much.
It's a very impressive display. Having myself worked on non-Markovian processes for a long time, I certainly find it very pleasing. I have one question. As you know, the memory effect Let's just pick that picture which you show quickly, wherein it looks like the sublevels, when the magnetic field is imposed, that it starts splitting, right? Originally, you have something more symmetric, and then as the memory increases, there seems to be sublevels appearing in a systematic way, right? So my question is that, well, apparently you can identify a particular non-Markov, the degree of memory or non-Markovianity, wherein this starts to show. Now, if I think about quantum mechanics, we could do that by imposing a magnetic field externally, let's say, right? So, and in that situation, there's a symmetry behind it, let's say in the z direction, the Zeeman effect, etc. Do you see a symmetry behind this purely from a dynamics viewpoint?
Well, so that's a very good question. It's a little bit early to answer. The interesting limit in this system is the infinite memory limit. It seems that in this infinite memory limit, there is a time symmetry. That was demonstrated recently by Mark Miskin. It's still unpublished.
It's a symmetry in what sense?
In the sense that you can reverse time.
Time reversal.
Yeah. So that's preliminary result. We don't. I mean, it has not been proved analytically yet. But maybe yes. Yeah. Sorry, you are the president.
Can you attribute a wavelength to your particles?
Sorry.
Like the Broglie wavelengths. Can you attribute a wavelength?
So I thought I would have a question about the Broglie, yes. So I've prepared. So in fact, yeah, okay, so as you know, that this is typically a pilot wave system. So there's no doubt about it. The wave is guided by the wave. So in the history, as you know, there have been two pilot wave models in quantum mechanics, one proposed by de Broglie initially, and then the one proposed by Bohm. And in fact, they look somewhat similar in the sense that in both cases the drop something is driven by a wave. And Bohm, as you know, uses a Madelung transformation of Schrödinger equation and gets the trajectory and gets the dynamics. And de Broglie at that time sort of protested, saying that it's not the same as his model. And the reason is that if you start from Schrödinger equation, you deal with probabilities, and therefore you get trajectories of probabilities. And what de Broglie said, what I had in mind is that a real wave is guided in the real space by a real wave. So in fact, he had the idea that there was, so he proposed, but with no sort of proof that there were two solutions. One solution that he called it a double solution, that there was a wave guiding the particle, which is of unknown nature, which is still of unknown nature nowadays. And that would be a real wave in the real space, and that the second solution would be the wave, which is a solution of Schrödinger equation. And so from this point of view, the two pilot waves differ. And in our system, we seem to have a situation which is closer to de Broglie in the sense that we have a real wave. And for instance, this is a simulation of what happens if you are diffracted through a slit. So these are the trajectories that you can do by numerical simulation with our type of wave. And as you see, trajectories are very complex in the slit region, which can be explained because in that region you excite sort of eigenmodes of the domain. And when they get out of it, then they move straight again. But in so doing, some of them have crossed the middle line. And this is the difference with Bohm solution. Bohmian solution never cross the middle line because they deal with probabilities. So there is very strong similarity yet, but there's still some differences. So this is rather the situation that we observe. So it seems that we are sort of, I don't know what else. Yes, so in fact, in our situation, we do see two ways. We see the wave that is guiding the particle through the slit. And then if you look at the result of the diffraction through a slit, you see a probability on the screen. And if you couldn't see, if you were in quantum mechanics, you would not be able to see any of this. But then you would see this probability. So in fact, if you want to imagine quantum mechanics in this experiment, you have to forget that you can see things, because in quantum mechanics, everything is quantum. So in our system, we would have a situation of that kind if we had only for doing measurements, waves or drops or walls. In that situation, we do recover the same uncertainties, the same problems of measurements. But fortunately, we have light, and light doesn't interact, and so we can look at what happens. So in a way, we have intrusive measurement and non-intrusive measurements.
Yves, have you tried to make experiments with two particles?
Yes.
Yes.
Well, we have tried a little bit.
Yes.
We have not tried yet the situation with central force, because it's difficult to get two identical drops with identical content of ferrofluids. But we are planning to do it. You have to work harder.
Okay, these last two questions. One,
Neighbor.
here.
Your memory is self-generated, as you say, but of course it's imposed by the boundaries of your container. Did you map out the dependence on the size of the container, either really changing sizes or changing points in phase space?
You're perfectly right. This is what we have to avoid. So, in fact, that's one of the limits of these experiments, is that we can't go to very high memory, because if we go to too high memory, then the waves touch the container, and for this central force experiment, for instance, this is no longer valid. So in our case, we take care, so it's a limiting factor, because we can't go to very, very high memory because of that.
How reproducible are your experiments? Suppose you repeat an experiment many times with exactly the same initial situation, initial conditions. How quickly does the motion randomize, start to become different after repetition?
Okay, so that's, okay, so the statistical properties are reproducible. For instance, if I do the same experiment in central force where I have this distribution between two states.
But you have a distribution, so it means that every time something
yeah, but if I do
happens.
the averaging for a long enough time, I will have exactly the same probability in each state.
No, but I was wondering what causes random behavior here. I mean, what are the random forces?
It's the intermittent behavior of the dynamics of the system. So it's intrinsically, it's like in nonlinear physics. You know, you reach chaotic states, yeah. But it seems that this chaotic state
it's like the butterfly effect which takes place.
Yeah,
so
but
very small
yeah.
initial changes make big.
But it's still intriguing because we have linear waves, but we have nonlinearity in the coupling to a point, to the bouncing on a point. So it seems that it is very similar to the butterfly effect, but not exactly in the same type of. It gives the same type of dynamics with the same type of intermittency, but maybe not exactly the same origin, because here it's linked with the memory.
Okay. Is it not like?
It is.
Is it not like something that in your theory I mean, not in the experiment, in the theory you have not included some random quantity, because no. I mean.
We have to add a little bit of noise to avoid numerical noise, but otherwise we don't need noise. It's spontaneously unstable.